So ASTRO-H is a Japanese X-ray telescope, but based on a satellite in space. And so that allows us to look at the universe in X-rays. So what does that mean? So ever since the dawn of mankind, we've been looking at the sky with our eyes, and then we got curious and we wondered, how can we look at it in different colors that our eyes can't see? We used infrared light. There's a lot of infrared light coming from the sky. Ultraviolet, also whole new things in the ultraviolet when you look at the sky. And then we've been using microwaves, looking at the sky in microwaves, radio waves, and then more recently using X-rays. The same X-rays that you use in a hospital to figure out if you have a fracture, but there are celestial bodies that emit X-rays. X-rays are super high energy radiation, and they're only emitted by high energy events. So it's the most kind of exciting, catastrophic things that emit X-rays, such as the death of stars, that massive explosion, or if you have a black hole gobbling everything around it, or at the center of galaxies. These things emit X-rays in the sky. There's a source of X-rays in the sky. So we've had a few space-borne telescopes like that, measuring X-rays over the last couple of decades, but so far they've always been kind of a little bit crude, so to speak, meaning very big pixels, only one color, so kind of a black and white, big pixel image. It's good, but not as good as ASTRO-H. ASTRO-H is going to be high definition color image. Color meaning we're going to measure X-rays of different frequencies, thanks to a spectrometer we call that can split the X-rays in different frequencies, and we're going to have very, very precise pointing, so we can have very, very small pixels in our image. So that will teach us a whole lot more about the X-ray universe, meaning about the high energy things in the universe. As for Canada, what have we done with this? So this is like a big teamwork, like a cooperative. In exchange for so that our scientists can have access to the data, we had to contribute something to the telescope itself. And our contribution was what we call a metrology system. So this telescope is huge. It needs to be very, very, very big for the detection of X-rays to work. It's too big to fit in the rocket. So it was folded up for launch and then hurtled into orbit, and then it deploys in space. But you can imagine when these things deploy, they're kind of lanky, and they tend to bend and twist and shake, and with the heat of the sunlight, they cool down, warm up, they kind of warp. So they don't stay straight. That's very bad for a telescope, to warp and not stay straight. So we contributed a system that measures how straight the telescope is, if it's warped, twisted, bent, all that, so that we can figure out ways to improve the image and then get the perfect X-ray image that we're seeking. And that way, we're kind of opening a new window on the universe, looking at it in very high resolution in X-rays.